Okay, Calc 2, Lecture 27, Parametric and Polar. Now, this is polar coordinates, and it is area and arc length. Now, arc length is easy, but the area is tricky. So, we need the differential of area, ds. Now, I'm using S for area. It's better to use S than A. So, differential of area, ds, if we can find differential of area, then when we integrate that, we have area. So let's look at a small portion of the area. So this is R, and R moves by d theta. So this is theta. I'm at the point, say theta, and this is r theta, and this is what? This is R. So this point A has coordinates r theta, and this point has coordinates r plus d theta, r plus dr, and theta plus d theta. Okay, so we have these 2 points, A and B, on a polar curve. Well, we might be confused what's going on. So this is like the polar curve, and these are the 2 points on the polar curve, the A and B. And I have moved by d theta, and r goes from r to r plus dr. Now, you might say, well, might be smaller, this one. That's okay, dr can be negative. Okay, so let's find this area. Now, since r and r plus dr are very close, I can assume that they're the same. So I end up with this triangle. So let's just rotate this and put it here. And this triangle, say, has sides OA and OB, and these are R and R, and this angle is d theta. Now, by just simple formula for area from trigonometry, the area is in fact this times sine of this angle divided by 2. So it is 1/2 OA times OB times sine of d theta. Now, OA and OB I assume that they are both R, so I wrote R and R. But why is this d theta? Why sine d theta is in fact d theta? Now let's go back to Calc 1 and an important limit. Remember, in Calc 1 we have limit of sine theta over theta as theta goes to 0 is 1. What does this mean? This means that as theta goes to 0, sine theta is approximately equal to theta, right? Which also means this, because d theta is what? D theta is small theta. That means, in fact, like theta goes to 0. So this implies that sine d theta is approximately equal to d theta. Okay? So this limit, in fact, uses something like that. But let me just say it here in this form, because I don't want to go too far into this. But when we get to Taylor series, you will see that a Taylor expansion of sine theta is in fact starts with theta. So that's another way to say it. Okay, now, so this is in fact ds. So ds is simply 1/2 r squared d theta. That's it. So it is 1/2 r squared d theta. So if we integrate this, we will get area. But what area are we talking about? So let me erase this and give you an idea what we're talking about. So if I have a parametric, polar curve, say something, and I go from point, say not point, this is theta 0 and this is theta 1, right? So I'm talking about this area of OAB, and let me put this on top. I'm not talking about the triangle, I'm talking about this section of this, what's that called? So I'm talking about this OAB with this side being a curve. Well, it can be a line, but in general it's a curve. So this is an area of OAB. We found that this should be from theta 0 to theta 1 ds. And so this is from theta 0 to theta 1, 1/2 r squared d theta. Okay, so area is in fact this, and that is this area. I'm talking about this area. Okay, so S in polar form is integral from theta 0, theta 1, 1/2 r squared d theta. And remember, r is given as a function of theta. R is a function of theta. So this whole thing is, the integrand is a function of theta. Okay, so that is formula for, say, area. Now, what is area between two curves? You can guess what that is. In fact, it is area of the outside one minus the inside one. So let me write down formula for area between two curves, which is what you will see a lot, even much more than just area for one curve. So if I have two of them, and I'm trying to find this area, A, B, C, D, and it goes from theta 0 to theta 1, and and this area is, so this one is R1, this one is R say inside, and this one is R outside, right? So R inside is some function of theta, and R outside is also some function of theta. Okay, so R in, R out. Let me draw this line. R in, R out. R I, R out. Okay. And I'm writing a formula for this area. Area of this thing. A, B, C, D. And let me put this on top, which I mean this side and this side are curves. Can be curves. So this area is in fact area of the outside minus area of the inside, or the other way, area of the inside minus that. So this is integral from theta 0 to theta 1, 1/2 r outside squared minus r inside squared d theta. Okay, and word of caution, this is one of those common mistakes that some of you have made in that first exam. It is r outside squared minus r inside squared, not r outside minus r inside squared. This is wrong. This is correct. So don't tell me that you didn't know. Yeah. So this is correct, not that. Don't write that. That's wrong and totally wrong. Okay, so that is in fact the area between two curves given in polar form. And as I said, this is what you will see a lot. Area between two polar form. But let me give you examples and of all types. So First is examples. One, area of a circle with radius r. So area of a circle with radius r, we can put this circle at the origin, say, and here radius r, and well, let's write capital R so you don't get confused with this thing. So let's say capital R. Okay, so what is polar, say, polar form of this thing, the function that this is its, say, graph, polar graph. So that is in fact this. This, remember, this is in fact constant function. Constant function is this. Its graph is this. So R equals R. This is in fact f theta equals this R, constant function. In polar form. Now, from 0 to 2 pi, if I go from 0 to 2 pi, I have gone through one rotation, and I need one rotation of this. If you go twice, then you're finding twice the area. So this area is in fact from 0 to 2 pi, 1/2 r squared d theta, and that is from 0 to 2 pi, 1/2. Remember, this is simply r, so I have r squared d theta, but this is just a constant, so I have 1/2 r squared integral from 0 to 2 pi d theta. This is theta from 0 to 2 pi, so that's in fact 2 pi, 1/2 r squared times 2 pi, which I will get pi r squared. So that's the famous formula. Area of a circle is pi r squared. And this is the easiest way to show that it is pi r squared. Remember, if I wanted to do this using rectangular coordinates, then I cannot just do the whole thing. I can find half of this, so area of half of this semicircle, so area of the semicircle would be from, say, minus r to r, and this top one would be y equals square root of r squared minus x squared, right? So I had to write this, r squared minus x squared dx. I'm not saying it's hard to find this, no, but it takes some time, and you need say trig substitution and blah 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 blah. So that's perhaps the easiest way to find area of a circle. You can do it here, but you need some extra work, but that's just the simplest integral you can get. So anyway, this is area of a circle when it's like this. Now what happens if we put it here? Two. So if I have this circle, and if I put it here, then this point will be r, 0, right? And remember, this has formula r equals 2r cosine theta. Okay? 2r cosine theta. If this is a, then the radius is a over 2. This is 2r, this point is 2r, so the radius is r. Now, this is important. Let's see. When we were graphing this, and you have to plot this thing on your calculator or somewhere like Wolfram Alpha or someplace. If you use Wolfram Alpha, just mention that this is polar coordinates. So we can say graph this thing in polar coordinates. Otherwise, it will give you a graph of 2r cosine theta in xy coordinate. which is like this, remember, that's just simple cosine. Well, anyway, so this is 2r cosine theta. When you graph it, check. First go with from 0 to I, that's what I would do if I have just simply theta, so I would go from 0 to pi, or maybe pi over 2. If I do that, I will get half of this. From 0 to pi, I will get the whole circle. So that's it. So this should be from 0 to pi. So the integral should be from 0 to pi, not from 0 to 2 pi. So S will be 1/2 r squared d theta, and let me erase this, and so that is, well, let me write the 1/2 outside, and I have from 0 to pi 2r cosine theta squared d theta. So that is 4r squared, and comes out I have 2r squared integral from 0 to pi cosine squared theta d theta, right? So that is, remember cosine squared was, so I have 2r squared integral 0 pi, cosine squared was 1/2 1 plus cosine 2 theta d theta. So this will be 2r squared 1/2 times 1 d theta from 0 to pi will be 1/2 pi. This one is 1/2, and 1/2, then there is a 2 here, so I will get 1/4 sine 2 theta from 0 to pi. This one is 0. Sine 2 pi is 0, sine 0 is 0, so the second one is 0, and what I will get is 2r squared times 1/2 pi, that is pi r squared again. We expected that, so we have pi r squared as area of this circle if I put it in this position. So now let's see, let's just make it more difficult. 3. Area enclosed by 2 circles. Now in this case it is by 2 circles, it can be anything. So, and if I give you something like this, which I will in about 2 weeks in an exam, I will plot the graph. So don't worry, you have the graph. The thing you should do is simply finding the limits of integrals. So in area, especially area in polar form, the most important thing is the limits of the integral when you're finding area between 2 curves. So, area between 2 circles, or enclosed by 2 circles. Let's say we have a circle with radius, say, 1, say. So let me put it here, 1. And let's have a circle with radius, say, I don't know, maybe, so this is point 1, let's say 2, 3, and 4. So if I put the center here, I will get a circle with radius 2. So if I put the center here, I have a circle like this. So let's say I want to find this area. Enclosed, it says enclosed. So this area is in fact this OAB, this. But you might say, I know, I can write this in, say, rectangular form and find it. But believe me, if you try, you will get 2 integrals which you have to use trig substitution. Okay, let's see. What is it? How do we find this? So this is area enclosed by these 2 So I have to look at this from here to here, for example, and then from somewhere here to this point, right? Because I have two things here to consider. But let's put it this way. Let's say, okay, instead of finding this, maybe I can find the other side, right? Maybe I can find this area which is on this side. But that's also not a good idea. Let's say we have, okay, so first thing we have to find these 2, point A and B. Let's see if I can, so this one is R equals R, this one, and this one is R equals, no, this is in fact 1, so it is R equals 1, not R. So let me just write 1. And this one has radius 2, so it is R equals 4 cosine theta. R equals 4 cosine theta. So I have to find these 2 angles, the points of intersection first. These 2 angles, let me use this color here, although I don't think it matters what color I'm using. You don't see the color here. And this one. So I have to find these 2 angles, say this one and this one. Okay? So because I'm going from theta, say something, whatever that is, theta 0 to theta 1, but again, there's also some part which is between, say, on this side it is between theta, whatever that is, to theta equals pi over 2. Okay, let's see if we can find this theta. So R equals 4 cosine and R equals 1. You would say, okay, these 2 points are equal, so we have the same R. Okay, yeah, that's correct. So let's write this. R equals R. R equals R when we are at points at A and B. Don't laugh at me. This means that this R equals this R. So I have 1 equals 4 cosine theta. So this gives me cosine theta is 1 over 4. So this theta, this one, theta 1 will be cosine inverse of 1 over 4. Whatever that is, let's just write theta 1. What is theta 2? Theta 2 is minus that, right? You can see theta 2 is minus this thing from the picture, minus cosine inverse of 1 over 4. So if I want to find this area, if I go from here to here and just use this, I will find just this say this section, OAB. Okay. So what happens to these two parts? Say OB something, whatever that is. Oh no. So and this side. So I mean these two, and then there's another one here like this. So if I go from theta 2 to theta 1, I will get this part of this circle. But I need these 2. But what, can I write minus? Let's see if minus really works. Can I, because this is minus something. So, to find this OAB, I need the area OAB, well, let me put something here, OACB. OACB, that is in fact integral from theta 2 to theta 1, 1/2 r squared d theta. Okay, so this is minus something, so this gives me the area, gives this area, gives this area. Okay, so let me, and what R should I use here? Oh yeah, let me write the R. So what R am I using? I'm using this, the R for this thing, which is simply 1/2 R squared d theta, right? So yeah, that is simple to find. In fact, it is 1/2 R squared times theta 1 minus theta 2. So it's like 2 theta 1, because theta 1 and theta 2 in absolute value, they are the same. That makes sense, because that you can even say from pre-calc that this area from pre-calc, what was that? That was 1/2 R squared times theta. But you have two of them, so you have 2 theta. So that makes sense even from pre-calc formulas. So that is this one. Now what happens to one of these areas, that simple one? So let me, not simple, that small one. Let me find some place to write this thing. Okay. So, let me draw a larger picture. So I have this OB, say, and remember these two are the same. They have the same area by symmetry. If they didn't have the same area, then you have to do 2 integrals, but find 2 integrals. But they have the same, so I have something like this. And theta starts at theta 1, ends where? Where do I get this point? So if I start at theta 1, let's look at this guy here. Do I have another picture? Yeah, I have. So, look at this. So let's move this. Let's go this way. So this starts here. If I move theta, then I'm here, then here, and I end up here, right? So when theta gets larger, from theta 1 to something, I will get this curve. So this curve goes this way, and goes to 0, right? And for what theta does it hit this point? Theta equals pi over 2. Okay, so starts at theta 1 and goes to theta equals pi over 2. So the area of this portion, area of OB, well, let me say some OB, did I use something C, a D? So let's say OBD. OBD. So this is in fact starting at theta 1, ending at pi over 2, 1/2 R squared d theta. What R is it? This R. This R. See, this is this one. So that is integral from theta 1 to pi over 2, 1/2 times 4 cosine theta squared d theta. Okay, so that is area of this OBD, and we have 2 of them, so this area will be twice this thing. So we have this area which we found as integral from theta 2 to theta 1, 1/2 R squared, was it? Yeah, R squared d theta, and plus 2 times integral from theta 1 to pi over 2, 1/2 R squared, this R squared, which is 4 cosine theta. Squared d theta. Okay, so that is the end result. which is this area enclosed by these two circles. Okay, now you said, gee, that was hard. Yeah, I'm not saying it's easy, no, but what was important here? Again, I'm telling you, these two, and also here. You have to graph it. You have to graph and see how does this shape, how should I say that? Where does it go? So you have to start at theta 1 on your calculator, or if you're doing one from offline, whatever, say graph it from theta 1 to say pi over 4 or something, I don't know. And see what happens. What part of the graph is in fact your calculator, what part your calculator gives you. And when you make sure that it is from, say, something theta 1 to pi over 2, then that's it, then you have it. And don't jump on RO minus RI immediately. No, you have to draw the picture and see for yourself. If you had just written, gee, I don't know if RO minus RI, what is RO minus RI? If I had done that, if I had simply written RO minus RI, RO squared minus RI squared, what would I get? Let me give it as another example. That is in fact this one, 4. For area outside how should I say that? Area outside this area outside R equals 1 and inside R equals 4 cosine theta. Okay, so this is example 4, and let me erase all this stuff here and show you what area I'm talking about. This is in fact the area that needs RORI. So I'm talking about this area. A, say B, C, D, E, say E, A, E, B. So that is this area, the area of this area. S of A, E, B, C. Oh yeah, okay. A, E, B, C. A, E, B, C, A. No, it ends at A. So that is, well, I guess I should write A, B, C, A here. So let's make sure that we're there. So A, B, A, E, B, C, A. Okay? Now, what is it? It is in fact between those two. It is RORI. As I said, it's not always RORI. You have to be careful. Graph it, and or if the graph is given to you, look carefully. So this is, let's say, what is RO and what is RI in this case? So this is R outside, and this is R inside, and now I have RORI. So this is, this area will be, this S will be integral. Where does it go? From theta 2 to theta 1, right? From theta 2 to theta 1, 1/2 R outside squared minus R inside squared d theta. Now, this one will be integral from theta 2, theta 1, 1/2. R outside is this, 4, 16 cosine squared theta. R inside is 1 squared d theta. So, calculate this and plug in theta 2 and theta 1. You can find them in an approximate value anyway, and you have this area, the approximate value of this nice area. So then RO squared minus RI squared is not always the case. You just look at the picture and ask yourself, what am I talking about? What is this talking about? So now, if I mistakenly write, for example, from some students write, instead of this, they use this one. They use the complement. I mean, if for example this is minus 30 degrees, they use 330. If I use from 330 to 30, what will that be? Because from 30, okay, so if I do that, if you do that, you will get a negative number. So let me, so this is theta 2 to theta 1, and this is theta 1. This guy here is theta 1 and pi. Okay, so if I write the integral this way, if I go from theta 1 to the complement of theta 2, which is, how should I write this thing? We put 2 pi, in fact, plus theta 2. Remember, theta 2 is negative. Theta 2 is this negative. So if I go from here to here, so this is from here to this thing. This is 2 pi plus theta 2. If I do this, I'm blah blah blah, the same thing. This is this area which is inside, this is area of the region outside r equals 4 cosine theta, inside r equals 1. So you see, you're finding this area on this side with just a small mistake. So if I'm looking for this area and you write it like this and say, well, it seems that it goes from here to here, and not from here to here, you just say, why should I go with negative theta? I can write this as this theta. This is the positive one. If you do that, you are going from here to here in this direction. And what does it give you? It gives you this area on this side. O, B, say, M, A. So this will be the area of O, B, M, A. This thing. O, B, M, A. This one. So be careful on those limits of integral when it comes to finding area between two curves in polar form. Now I have given, in fact the book has enough examples, and I also have given you enough examples in those notes that I posted. So just take a look at the notes. Now, there was another thing, arc length. So that was area, and I guess that's enough for area. Arc length is very simple, but we had arc length. What was arc length in parametric form? Parametric form, it was L was from say T1 or T0 to T1 something, and here we had the square root of dx dt squared plus dy dt squared dt, right? Now we know that we can write equation, parametric equation, given r equals f theta. The parametric form of this is, in fact, remember, x is r cosine theta and y is r sine theta. So the parametric form will be f theta cosine theta and f theta sine theta. So everything is in terms of theta, and theta is parameter. Now what do I need? I need dx dt and this one dt. So this gives me, and this gives me, let me write them, dx dt will be derivative of this one times this one plus derivative of this one times this one, right? So I have f prime, let me just write f prime cosine theta minus f sine theta, and dy dt will be again derivative of this times that, that's f prime sine theta plus f cosine theta, right? So that is derivatives, and now I have to square them and add them. So let me write here, square them and add them, and I have this thing. So dx dt, this is theta, right? Because the parameter is theta, so that should be d theta. So dx d theta squared plus dy d theta squared. Okay, let's square them. This is f prime squared cosine squared. Well, I'm right. So this one will be f prime squared cosine squared minus twice this one times this one, which is minus 2 f prime f sine theta cosine theta plus this one squared f squared sine squared theta plus the second one will be f prime squared sine squared theta plus this time 2f prime f sine theta cosine theta plus f squared cosine squared theta. So if I add them, I will get f prime squared sine squared plus cosine squared is 1, this one cancels, and that one is again f squared. So I got two interesting, I got an interesting and simple formula, and that is this thing. So the arc length in polar form will be integral from, say, theta 0 to theta 1 and square root of f prime squared plus f squared d theta. Okay? So that is arc length. I will let me give you two examples of this. Let me erase this. And I will give you examples of circles, say. As I said, and I say it again, this integrand is not always a simple integrand. In many cases, it's just amazingly hard. So, examples. One, again, find circumference of a circle with radius r. Okay, so I just put the circle in the middle again, O. So this is r equals r, and that's my function f theta. Remember, constant function. So L and I need 0 to 2 pi, right? I need 0 to 2 pi in my case. In this case, in fact, one round is 0 to 2 pi. That covers everything. So that is 0 to pi. The integrand f prime is 0. F itself is r squared. D theta, right? So square root or radical r squared r is a positive number, so that's r. So in fact it is 0 to pi r d theta, which is r theta from 0 to 2 pi, and that is 2 pi r. Remember? So I got back to the arc length. And I guess I also calculated arc length using parametric equation. So you see that using polar coordinates and polar equation of a circle, this becomes a simple integral. Now let's do this again, but using something else, using the other circle, okay? So let's put the circle in a different position. So if I put the circle in this position here, or up there, no difference, then if this has radius r, then this point is r over 2, 0, and this is r equals r cosine theta, right? And this is r. Always this r equals from 0, 0.0 to this point of the circle. Okay, so I need, then that's f theta. I need f prime theta. F prime theta is minus r sine theta, right? Okay, so we have arc length. Arc length will be integral. Now, what are the limits? If I start at 0, pi over 2, I'm here, pi, I'm here. So it's 0 pi, not 2 pi, 0 pi. And f prime is r, that's r squared, sine squared theta. F squared is r squared, cosine squared theta, and d theta. So this will be just simply r squared, radical r squared. I have just r. So 0 pi. I have r d theta. Okay. So that will give me pi r. What are? I should get 2 pi. I can't see what. Oh, gee. I know. This is the radius r should give me 2r here, right? Radius r. This was radius r over 2. So if this is point r, then this is point 2r. So I have 2r as f theta. So this is minus 2r. And I have 4r squared and 4r squared here. So I will get 2r, and that's 2 pi r. Right? Yeah, I told you what this thing is, and I made a mistake myself. So if that was when the radius was r over 2, not r. If the radius is r, this point is 2r. This point on the x-axis as the x-coordinate is 2r. So this should be 2r cosine theta. Why is it? Because for theta equal to 0, I will get 2r. So this point has coordinates. This is all. This point has coordinates. Say r theta r will be 2r and 0 for the angle. So for 0 cosine 0 is 1 and r will be 2r. So this point is 2r 0, and also if you go the other way you will get minus 2r and pi, right? So this also can be written as minus 2r and pi. Okay, so you can say that one reason I use this is because when you go back one round, you're still at that point, and that the coordinate, since theta is pi, the coordinate is minus 2r pi. It's not 2r pi. 2r pi, where is 2r pi? 2r pi is on this side. This is 2r comma pi, this point. Right, because pi is this way, pi is this way. So this is the terminal side for pi, the positive terminal side for pi. So this is 2r and pi. This is the negative terminal side, so it is minus 2r pi. Okay. So that is the circumference of a circle using two different, say, positions for that circle. And be careful when you write down the equation. Look at this point on the x-axis, and that comes here. Okay, so that was the chapter on polar coordinates, polar and parametric, and next will be chapter 11, and that is next time.